In the darkness between the stars, there may be worlds with no sun, no sunrise, and no home. These are rogue planets, lost from their systems and drifting alone through deep space. Some may be colder than anything familiar. Some may still carry hidden heat beneath the dark. Tonight, the journey follows these silent worlds and the science that reveals them. If this kind of deep space story belongs on the channel, please like the video and subscribe. Far from the bright paths traced by ordinary planets, the Milky Way contains another kind of world. These are rogue planets, planetary mass bodies that move through space without circling a star. They do not rise and set around a sun. They do not share the familiar arrangement of system, orbit, and seasonal light. They exist instead as solitary members of the galaxy, carried through the long dark between stars. In the widest view, they belong to the same great stellar city as every sun, cloud, cluster, and nebula in the Milky Way, yet they remain among its most hidden inhabitants. Their presence suggests that a galaxy is not made only of shining stars and the planets that keep close to them. It also holds lost worlds, dim wanderers, and bodies so faint that most of them pass unnoticed through the dark. Astronomers describe a rogue planet as a free-floating planetary mass object. The phrase is careful because the boundary between a true planet and a very small brown dwarf is not always easy to fix from a distance. A brown dwarf is an object more massive than a giant planet, but not massive enough to sustain the steady hydrogen fusion that powers a star. Some solitary worlds seem to fall below that boundary and have masses comparable to known planets. Others sit close to the dividing line, where origin matters as much as mass. A world that forms around a star and is later cast out fits easily into the common idea of a rogue planet. A body that forms alone from a collapsing cloud may resemble a planet in mass but differ in origin. At the scale of the whole galaxy, these categories blur together, and the sky does not always reveal how a lonely world began. This uncertainty makes the population of rogue planets difficult to count. In ordinary planetary systems, a host star provides a reference point. It shines, it anchors motion, and it helps reveal the worlds around it. A rogue planet offers none of that assistance. It reflects almost no light that can be easily seen across interstellar distance, and many of them emit only weak heat. Against the enormous background of the Milky Way, a small cold world becomes nearly invisible. Even when astronomers infer that such bodies are present, they often detect only a hint or a faint glow. The galaxy is therefore likely to contain many more rogue planets than the number already identified. Observations indicate that free-floating planetary mass objects do exist in meaningful numbers. It remains uncertain how numerous they are across the full Milky Way. In this widest region of the subject, the main setting is the galaxy itself. The Milky Way is a barred spiral galaxy with a broad disk of stars, gas, and dust, spiral arms rich in star formation, and a more diffuse halo surrounding the main luminous structure. Within this system, stars travel in long galactic orbits over immense spans of time. Rogue planets share that larger motion. Even without a parent star, they remain bound to the gravity of the galaxy unless some rare encounter sends them beyond it. They drift through spiral arms, through sparse regions between stellar groups, and through clouds where new stars begin to form. Some likely spend ages in deep darkness far from any bright source. Others may cross regions where nearby stars briefly brighten their skies before fading again as distance opens. At the galactic scale, they are participants in the same vast circulation that carries all material through the Milky Way. This galactic view also changes the meaning of the word lost. A rogue planet is lost only in relation to a star. In relation to the Milky Way, it still belongs somewhere. It occupies a path, holds mass, responds to gravity, and takes part in the slow, dynamical life of the galaxy. Its history may include close passages near stellar nurseries, ancient clusters, or crowded planetary systems. Its future may involve continued motion through the interstellar medium, the thin spread of gas and dust that lies between stars. The interstellar medium is extremely diffuse matter distributed across galactic space. For a rogue planet, this medium is not a weather system in the ordinary sense, but it is still the surrounding environment. The planet moves through that environment just as a star does, though with far less light announcing its presence. The current census of rogue planets reflects both progress and limitation. Over the past decades, astronomers have found evidence for individual free-floating planetary mass objects and for groups of them in young regions of the Milky Way. These discoveries have established that starless worlds are not merely theoretical. They are part of the real galactic population. Yet every estimate carries uncertainty because detection favours special circumstances. Warmer young objects are easier to notice than older, colder ones. More massive bodies are easier to distinguish than smaller ones. Objects in certain locations reveal themselves more readily than those in the wider dark. A catalogue built from such conditions cannot immediately represent the full hidden population. It shows only the fraction that current instruments and methods can reach. For this reason, rogue planets occupy an unusual place in modern astronomy. They are no longer speculative in the basic sense, because observations have moved them into the realm of known objects. At the same time, they remain elusive enough that the galaxy may hold far more than present surveys show. Some studies suggest very large numbers of free-floating worlds, while other work points to more modest counts depending on the mass range and region observed. The disagreement does not mean the objects are doubtful. It means the census is still incomplete, and the conditions of discovery matter deeply. Astronomers can state with confidence that the Milky Way contains solitary planetary mass worlds. They cannot yet provide a final total for the entire galaxy. Seen from this outermost perspective, rogue planets add quiet complexity to the Milky Way. A galaxy already contains brilliant stars, collapsed remnants, giant gas clouds, dust lanes, and orbiting systems filled with moons and planets. Rogue planets extend that inventory into a colder and less visible domain. They represent planetary matter without a household star, motion without a regular year, and existence defined more by the galaxy than by a local sun. Their importance begins here, at the widest scale, as a reminder that planetary worlds are not confined to neat systems of light. Some belong to the dark spaces in between, where the Milky Way carries them onward without ever making them easy to see. Across the crowded background of the Milky Way, countless stars shine at enormous distances from one another and yet appear close together to the human eye, in dense galactic fields, especially toward the central regions. Their light forms a deep and layered backdrop that seems almost continuous. This crowded background matters because a rogue planet is usually too faint to be seen directly. It does not announce itself by bright reflected light, and many are too cold or too small to stand out by their own heat. Yet when such a world passes through the line between Earth and a distant star, gravity provides another way for it to appear. The planet remains dark, but the space around it does not behave as empty. Its mass slightly bends the path of light, and for a brief interval a background star can seem brighter than usual. In that short alteration of starlight, a hidden world leaves its trace. This effect is called gravitational microlensing. A gravitational lens is any mass that bends light by gravity. In this case, the lens is small on cosmic terms, often no more than a planet or star, and the change in brightness is temporary and subtle. The distant star does not physically brighten. Instead, the light already leaving it is redirected in a way that sends more of it toward the observer for a limited time. The alignment must be unusually precise. The rogue planet, the far star, and Earth do not need perfect symmetry, but they must pass close enough to a single line of sight for the bending to matter. When that happens, the hidden object acts briefly like a natural lens. The event passes, the starlight returns to its earlier level, and the dark lens continues on its way. At the level of this outer detection zone, the crucial setting is not the rogue planet itself, but the sea of stars behind it. Astronomers watch vast numbers of distant stars because any one of them might be lensed by an unseen foreground object. A single isolated observation would reveal almost nothing, since ordinary stars also vary for many reasons. What matters is the pattern. Microlensing produces a smooth, characteristic brightening and fading shaped by geometry and motion, rather than by the inner activity of the star. The event is not a flare, not an explosion, and not an eclipse. It is a temporary amplification of background light, caused by the gravity of something dark passing in front. The planet is not seen as a disk or point of reflected light. It is inferred through the behavior of the star behind it. The timescale of the event helps indicate the mass of the lens. A more massive lens generally creates a longer event, while a smaller planetary lens often produces a shorter one. For rogue planets, this can mean a signal lasting from hours to days rather than weeks or months. This brevity is part of the difficulty. Astronomers must monitor dense star fields repeatedly and with great precision, because the signature can begin and end quickly. If observations are too widely spaced in time, the event may be missed or only partly recorded. A rogue planet therefore reveals itself not through brightness alone, but through timing, coverage, and careful statistical work across enormous numbers of stars. In practice, this means that the search for rogue planets becomes a search for rare and fleeting changes embedded within a constantly observed background. The background star fields most useful for microlensing are often those where the line of sight crosses a rich concentration of distant stars. The galactic bulge, the dense central region of the Milky Way, is one important example. There, many stars lie stacked along the same general direction, increasing the chance that a foreground object will pass near the line of sight to one of them. The greater the number of watched stars, the greater the chance that one will undergo a measurable lensing event. This is why surveys often focus on crowded stellar regions rather than empty parts of the sky. The method depends on probability. A rogue planet may travel silently for immense spans without ever aligning with a visible background star from Earth. Detection arrives only when chance geometry cooperates. Microlensing has a further quality that makes it especially valuable for rogue planets. It does not depend strongly on the light of the lens itself. Other detection methods in planetary astronomy often rely on a host star or on the planet's own emitted or reflected light. A rogue planet usually offers very little of either. Microlensing instead depends on mass. If the alignment is favourable, even a dark and distant object can be found because gravity still acts. This allows astronomers to detect worlds that would otherwise remain hidden from view. It also means the method is sensitive to solitary objects drifting through interstellar space, not only to planets bound to stars. In this sense, microlensing opens a window onto a part of the galactic inventory that ordinary imaging often misses. Even so, the method does not make rogue planets easy to study in a complete way. A microlensing event is usually not repeatable. Once the alignment passes, the same configuration does not return on human timescales. The observer cannot simply wait for the signal to come again tomorrow night. Because of this, each event carries special weight. Astronomers extract as much information as possible from the shape and duration of the brightening, from the precise motion of Earth, and from observations taken by different instruments at different locations. In some cases, these combined measurements allow researchers to estimate the mass and distance of the lensing object more securely. In many others, the event still leaves some ambiguity. Observations indicate that microlensing can reveal isolated planetary mass bodies. It remains uncertain in some individual cases whether a detected lens is fully unbound, loosely associated with a distant star, or part of a more complex system not easily seen. This uncertainty belongs to the method itself, not because it is weak, but because it is indirect. The lens is inferred from what it does to light, rather than from a clear direct image. Yet this indirectness is also its strength. It allows gravity to speak where light is absent. A rogue planet may drift unseen through the galactic dark, but when it crosses the face of a more distant star from Earth's perspective, the distant star briefly changes its appearance. In that moment, the background of the Milky Way becomes more than scenery. It becomes the instrument of discovery. The dense star fields of the galaxy provide the illumination, gravity provides the lens, and time provides the narrow window. Through this combination, solitary worlds that do not shine like stars and do not orbit like ordinary planets enter astronomical knowledge for a moment before the dark closes around them again, away from the crowded background fields used for microlensing. Another part of the galaxy offers a different path to rogue planets. These are young star-forming regions, places where stars and smaller bodies have only recently emerged from clouds of gas and dust. A star-forming region is a concentration of material where gravity gathers matter tightly enough for new objects to take shape. In these places, time itself becomes an observational advantage. A newly formed free-floating world has not yet released all of the heat carried from its birth. It still glows faintly, not with the blazing light of a star, but with a soft warmth that can be measured in infrared light. Infrared light is light associated with heat beyond the range of ordinary human sight. For rogue planets, this lingering warmth can make the difference between invisibility and detection. At the broad galactic scale, many rogue planets likely spend most of their existence growing colder and dimmer. Once they drift for long spans through interstellar space, their faint heat becomes harder to separate from the dark around them. In very young regions, however, the situation is different. The objects there have not yet had long ages to cool. Their interiors still carry the energy of contraction and formation, and that energy leaks outward through their outer layers. The result is a weak but detectable glow. It does not come from steady nuclear burning. Because these worlds are not stars, it comes from stored heat escaping gradually into space. For astronomers searching for isolated planetary mass bodies, youth creates a temporary window during which even a starless world can be seen more directly. The environment of a young region supports this method in several ways. First, the ages of the objects are relatively small by astronomical standards. Instead of billions of years, they may be only millions of years old. That difference is decisive because cooling is strongest early on, when a newly formed body loses heat from its outer layers and slowly settles into a dimmer state. Second, the region often lies near enough to Earth for sensitive telescopes to detect faint sources within it. Third, the young stars and substellar bodies in such a region usually share a common motion through space, which helps astronomers judge whether a faint object truly belongs to that group rather than merely lying by chance along the same line of sight. The region therefore provides not only bodies that are still warm, but also a shared context that helps sort members from unrelated background objects. This shared context matters because a faint red source on its own does not immediately reveal what it is. It may be a distant star, a brown dwarf, a background galaxy, or a young free-floating object of planetary mass. To tell the difference, astronomers combine the color of the source, its brightness, and its motion across the sky with estimates of the region's age and distance. If the object moves with the young association and has a brightness consistent with a very low mass at that age, it becomes a candidate rogue planet or free-floating planetary mass object. The conclusion is cautious because the estimates depend on models of early cooling and atmospheric behavior. Observations indicate that young regions contain many such low-mass isolated bodies. It remains uncertain in some cases exactly where each one falls on the line between planet and brown dwarf. At this stage of the search, the visual character of the sky changes. In microlensing work, the important image is a field crowded with distant background stars, watched for brief changes in brightness. In a young region, the important image is often a textured cloudscape of starbirth, mixed with infant stars, dust, and dim red sources embedded within or around the association. The rogue planet is no longer found by a passing event alone. It may appear as a real point of faint emitted light. This does not make it bright in an ordinary sense. Even young isolated worlds remain extremely dim compared with stars. But it means astronomers can search for them as objects that glow by their own leftover heat, rather than only as masses that reveal themselves indirectly. The youth of these regions also means that many of their members are still settling into final form. Gas clouds fragment, stars emerge, disks surround some young suns, and a wide range of low-mass bodies appears alongside them. In that setting, a solitary planetary mass object is easier to interpret as part of a broader birth environment, rather than as a fully ancient wanderer whose history has been erased by time. The region preserves some memory of origin simply because it is young. The objects within it have not yet travelled far from the conditions of their formation. For rogue planet studies, this is valuable, because the same place that makes the objects visible also preserves clues about how such objects arise in the first place. Yet within this section, the main importance of the region remains observational. Youth gives off heat, and heat gives astronomers light to measure. Infrared observatories are especially important here because warm young bodies radiate much of their energy at infrared wavelengths. Space telescopes and powerful ground-based instruments can detect this faint emission and compare it across large samples of objects within a region. Astronomers then use models of cooling to connect observed brightness with likely mass, always with care because the youngest and lowest mass bodies remain difficult to model perfectly. A small difference in age can alter the inferred mass. A cloudy atmosphere can change the measured light. Dust in the region can redden and dim the source. Even so, young associations remain among the most productive places to search for free-floating planetary mass objects by direct observation. In the widest sense, these regions act like temporary lanterns within the Milky Way, not because they are quiet, but because they allow dim, isolated worlds to stand out before age carries them into deeper obscurity. A rogue planet that is newly formed or newly revealed in a young association has not yet cooled into the nearly invisible state that likely defines much of its later existence. It can still be counted, measured, and compared. The galaxy contains many dark wanderers, but in these young regions some of them are still warm enough to declare themselves faintly against the surrounding black. That brief glow makes youth one of the most important outer conditions in the study of rogue planets, before the long drift through deep space becomes dominant. There is this earlier galactic setting where starless worlds are easier to find because they still carry the warmth of beginning. Within the wider category of young star-forming territory, the regions of Upper Scorpius and Ophiuchus stand out as one of the clearest places where a substantial population of rogue planets begins to emerge from the dark. These neighbouring regions lie relatively near the solar system on the scale of the Milky Way, and both are young enough that low-mass free-floating objects still retain detectable warmth. Together they provide a natural laboratory in which astronomers can search not only for individual solitary worlds, but for a broader population that can be counted, compared, and placed into a local census. At this stage, the story remains in the outer domain of the galactic setting, but the focus narrows from young regions in general to a particular nearby complex where starless planetary mass bodies are found in unexpectedly large numbers. Upper Scorpius is a young stellar association, a loose group of stars that share a common origin and motion through space. Ophiuchus, nearby, includes denser star-forming clouds where very young objects are still present among gas and dust. These regions are related in age and location closely enough that they can be studied together for certain purposes, especially when astronomers seek faint bodies that may belong to the same broad youthful environment. Their importance comes from a simple combination of factors. They are young, so low-mass objects remain warmer than older ones. They are near enough that faint sources can still be measured with sensitive instruments. They cover enough sky and contain enough members that a systematic survey can reveal patterns rather than isolated curiosities. In such a place, rogue planets are not merely rare surprises. They begin to appear as a population. When astronomers survey these regions, they do not simply look for darkness. They search for very faint points of infrared light, then compare those points across multiple observations and wavelengths. The first task is to identify sources whose color and brightness match what would be expected from extremely low-mass young objects. The second task is to separate genuine regional members from unrelated background stars and galaxies. The third task is to test whether the candidate objects share the same motion across the sky as the known young population. This process is demanding because each faint source can mislead. Dust can alter apparent color. Distance can alter brightness. Background objects can imitate the appearance of a young low-mass body. The resulting census is therefore built slowly, with care, through repeated comparison and filtering, in Upper Scorpius and Ophiuchus. This work has produced one of the most striking results in the study of rogue planets. Surveys of the region have identified at least 70 candidate free-floating planetary mass objects, with the possibility that the real number is considerably larger. This matters not only because the number is large, but because it emerges from a coherent young environment rather than from disconnected, isolated detections. A single rogue planet can always be treated as unusual. A group of them in the same broad region suggests that solitary planetary mass worlds may be a normal outcome of whatever processes operate there. The census remains incomplete, and not every candidate carries equal certainty, but the scale of the population is enough to shift the discussion away from rarity alone In this nearby complex, the Milky Way appears able to produce or retain many such objects. The word candidate remains important. A candidate is an object that fits the observed profile of a young free-floating planetary mass body, but may still require further confirmation. Astronomy often moves by degrees of confidence rather than by instant certainty, especially at the faintest edge of detection. Some candidates will later be strengthened by improved motion measurements or spectroscopy. Spectroscopy is the analysis of light divided into its component wavelengths, which can reveal temperature, composition, and surface gravity. Other candidates may prove to be slightly more massive than first thought, placing them closer to the brown dwarf category. Some may turn out to be contaminants from the background. Even so, the broad picture remains stable. These regions contain a remarkable number of very low-mass free-floating objects, many of them plausibly in the planetary mass range. The age of the region is central to this census. In older parts of the galaxy, comparable objects would be much harder to detect because they would have cooled and faded. In Upper Scorpius and Ophiuchus, youth still leaves a visible signature in infrared light. The census is therefore not a complete inventory of all rogue planets that exist there in an absolute sense. It is a count made possible by the fact that the objects are still warm enough to register. This also means the census must be interpreted with caution. It tells astronomers that a substantial population is present, but it does not immediately reveal the full hidden total of colder or fainter bodies that current observations cannot yet recover. The counted population is real, while the unseen remainder remains uncertain. Another important feature of this regional census is that it ties rogue planets to a recognizable local structure in the Milky Way. Instead of imagining solitary worlds as scattered randomly through immeasurable darkness, astronomers can point to a nearby youthful complex and say that here, in this defined part of the sky, they appear in notable abundance. This gives the subject a firmer observational ground. The worlds are still faint, still difficult, and still partly uncertain in classification, but they are no longer only abstract drifters in a general galactic background. They belong to a mapped region with known stars, known clouds, measured ages, and shared motion. That shared setting makes the census stronger because each candidate is judged not in isolation, but in relation to the population around it. The result is a quieter but deeper change in perspective. Rogue planets stop seeming like rare accidents glimpsed only by chance, and begin to look like one thread within the fabric of young stellar environments. Upper Scorpius and Ophiuchus do not resolve every uncertainty. They do not provide a final answer about the total number of rogue planets in the galaxy, nor do they settle every question of origin or classification. What they do provide is a nearby region where the count rises high enough to matter, and where the presence of many solitary planetary mass bodies can be studied as a population. In the outer structure of this script, that is the full meaning of this region. It is the place where the general idea of young glowing rogues becomes a measurable census, and where the Milky Way reveals that the dark between stars may hold far more worlds than older astronomy once imagined. Around a young star, the outer galactic setting gives way to a more local and structured environment. A broad disk of gas and dust surrounds the star during the early part of its life, and within that disk the ordinary story of planet formation begins. This is the region where many worlds first take shape before any later history separates them from their parent systems. The disk is not empty space. It is a flattened or rotating spread of material left over from star formation, with fine dust grains mixed among gas and ice. At first it appears diffuse and soft, but over time it becomes a place where tiny particles meet, cling, settle, and slowly organize matter into larger forms. In this section, the focus remains fully within that birthplace. The subject is not yet a wandering world in darkness, but a planet in the making, embedded within the disk around a young sun. A protoplanetary disk is the usual name for this structure. It forms because a collapsing cloud of gas and dust does not fall straight inward without motion. As the cloud contracts, rotation causes material to spread into a flattened shape around the growing star. The central star becomes the dominant mass, but the surrounding disk still contains the raw ingredients for planets. Dust particles made of silicates, carbon-rich compounds, metals, and frozen materials move within the gas, collide gently, and sometimes stick together. At the smallest scale, this process depends on contact forces, electrostatic attraction, and the simple chance of repeated encounters. A dust grain becomes a cluster becomes a pebble, and a pebble becomes part of something larger. The growth is slow and uneven, but the direction is clear. The disk provides both the material and the orbital setting in which planets can begin. The early disk is not uniform. Conditions change with distance from the star. Closer in, temperatures are higher and volatile substances such as water and other simple compounds are less likely to remain frozen. Farther out, colder conditions allow ices to survive. This difference matters because ice adds solid mass, and solid mass helps bodies grow more quickly. The result is a disk with distinct zones of available material, even if the boundaries between them are gradual rather than sharp. Dust density also varies, and turbulence within the gas can concentrate particles in certain places. These variations shape the speed and style of growth. A planet does not emerge from a smooth and identical environment at every distance. It forms within a layered structure where temperature, composition, and density guide what can gather and how fast it can happen. As particles grow beyond dust and pebble size, gravity begins to matter more strongly. Small bodies can attract nearby material, and repeated collisions may build them into planetesimals. A planetesimal is a solid body large enough for gravity to influence its accumulation in a meaningful way. Though not yet a planet, these bodies may be irregular at first, but they represent a major transition. The disk no longer contains only loose grains and drifting pebbles. It now contains small worlds in the earlier sense, each moving on its own orbit around the star and interacting with surrounding material. Some collide and merge, some break apart, some continue sweeping up smaller particles as they travel. Over time, a fraction of them become planetary embryos, larger growing bodies that dominate their local zones within the disk. This stage remains delicate and complex. A forming planet is not a finished object waiting quietly in place. It competes for material, experiences changing drag from the gas, and shares the disk with many other growing bodies. In the inner parts of the disk, rocky embryos may emerge where metals and silicate materials dominate the solid inventory. In the colder outer parts, icy solids increase the available mass and can help produce larger cores more rapidly. If a growing core becomes massive enough while gas still remains abundant in the disk, it may begin to gather a thick envelope of hydrogen and helium. In that case, a giant planet can form. If the gas disperses before this happens, the result may instead be a smaller rocky or icy world with a thinner atmosphere or none at all. The final outcome depends on timing as much as on raw mass. Gas does not remain in the disk forever. Young stars emit radiation and energetic particles, and the disk gradually evolves through heating, accretion, and dispersal. Accretion is the process by which material falls inward and becomes part of a larger body. Some disk material spirals toward the star, some becomes part of planets and smaller remnants, and some is driven away. This means planet formation occurs within a limited interval. The disk is a temporary structure, not a permanent one. Worlds must grow while the ingredients remain available. That temporary nature helps explain why planetary systems can differ so widely. A slight difference in disk mass, lifetime, turbulence, or temperature structure may alter what kinds of planets form and where they finish. The birthplace is therefore not only a source of material, it is also a changing environment with deadlines built into it. Observations of young stars across the Milky Way support this picture. Astronomers see disks around many young stars, and in some cases those disks show rings, gaps, spirals, and other structures that suggest active planet formation. Telescopes sensitive to infrared and radio wavelengths can detect dust and gas within these systems and trace how the material is distributed. These observations do not watch a single planet form from beginning to end on human timescales, but they reveal many disks at different stages, allowing astronomers to assemble a broad physical sequence. The evidence indicates that planet formation is not unusual. It is a common process in the life of stars born with surrounding disks. This matters deeply for rogue planets because before a planet can become solitary through the familiar route, it first has to exist as a normal product of disk formation around a star. Within this birthplace, a planet is still part of a system. It shares the star's gravity, the disk's motion, and the company of other growing bodies. Its orbit, composition, and mass emerge from the surrounding environment rather than from isolation. The disk shapes the planet from the outside inward. First by supplying solids and gas, then by controlling temperature, chemistry, and the pace of growth. In the calm language of formation, a rogue planet is not born rogue in this standard pathway. It begins as an ordinary planet forming in an ordinary disk around a young star, following the same broad rules that build the known worlds of many planetary systems across the galaxy. This section ends fully within the birthplace, where dust gathers, gravity strengthens, and a future planet first acquires form. Once several growing planets share the same young system, the calm structure of the disk can give way to a more restless gravitational order. A planetary system is not automatically stable simply because planets have formed within it. Each world exerts gravity on the others, and when large bodies occupy nearby or crossing orbital zones, their repeated influence can slowly alter the entire arrangement. In this section, the focus remains entirely on that unstable stage, when a once-ordered system begins to rearrange itself and some planets are driven outward beyond return. The rogue planet here is not yet defined by the deep dark between stars, but by the violent local process that removes it from its birthplace. This is the region of scattering, close encounters, and final expulsion. A young planetary system may begin in a crowded condition. Giant planets can form at different distances from the star. Smaller bodies may remain between them, and leftover debris can still circulate after the main gas disk thins or vanishes. While the disk remains present, gas can damp some orbital extremes and help maintain relative order. As that gas disperses, the system loses part of its stabilizing medium. What remains is a set of massive bodies orbiting the same star, each carrying momentum and each responding to the gravity of all the others. If their spacing is too tight, or if migration during formation has placed them in a delicate arrangement, the system may enter a phase of dynamical instability. Dynamical instability means that small gravitational changes grow with time instead of fading away, leading to major orbital rearrangement. This process often begins quietly. A planet may pass another at a distance that seems large on human terms, but small in gravitational terms. The encounter changes their path slightly. One may move into a more elongated orbit. Another may shift inward or outward. These changes then alter the timing and geometry of later encounters. What was once a near miss becomes a closer pass on a later orbit. The cumulative effect can become powerful because gravity acts repeatedly. Not only once. In a crowded system, a sequence of such interactions may continue over thousands, millions, or even longer spans of years, depending on the masses and spacing involved. The system does not explode outward in a single moment. It reorganizes through repeated exchanges of energy and angular momentum until one or more planets are pushed onto radically different paths. Angular momentum is the tendency of an orbiting body to preserve its rotational motion around a central point. In unstable systems, planets can exchange angular momentum through repeated gravitational encounters. One world may lose it and fall inward to a tighter orbit. Another may gain it and move farther out. Energy is also exchanged. A planet that receives enough orbital energy from encounters can be driven onto a path so stretched that it no longer remains permanently bound to the star. At first, the orbit may become extremely elongated, carrying the planet very far from the system before it returns. If later encounters add still more energy, the path changes from a bound orbit to an unbound one. At that point, the planet no longer circles the star at all. It escapes. This escape is the core event in the standard ejection route to a rogue planet. The star remains behind, still holding the rest of the system or what survives of it. The expelled world departs on a trajectory that no longer closes back into an orbit. In physical terms, it has exceeded the energy needed to remain gravitationally attached to its host star. The local system may keep changing after that, but for the ejected body the decisive transition has already occurred. It is no longer a planet of that star in the ordinary orbital sense. It has become free-floating. The transformation does not require the planet to break apart, change composition, or lose its planetary mass. What changes is its dynamical status. It passes from membership in a stellar system to solitary motion through the galaxy. Giant planets are often central to this process because their strong gravity can scatter other worlds efficiently. In systems with multiple massive planets, close interactions may fling one giant outward while another moves inward. Smaller planets and planetesimals can also be disturbed, sometimes colliding with the star, sometimes being thrown into distant reservoirs, and sometimes being expelled entirely. The exact outcome depends on masses, timing, initial spacing, and the remaining structure of the young system. Observations of exoplanetary systems support the view that migration and instability are common parts of planetary evolution. Many known giant planets occupy orbits very different from those in the solar system, suggesting that major rearrangement has occurred in at least some systems. Ejection is therefore not an exotic theoretical curiosity. It is a plausible natural result of ordinary gravitational mechanics acting in crowded planetary families. The expulsion stage can also involve resonance breaking. A resonance is an orbital pattern in which planets exert repeated gravitational effects on one another at regular intervals because their orbital periods are related by simple ratios. Resonances can sometimes stabilize a system, but they can also become fragile if migration mass growth or outside disturbance alters the balance. Once a resonance breaks, encounters that were once avoided may begin to occur, and instability can grow rapidly. In this way, a system that appeared ordered for a time may eventually become destructive for one of its members. The history of ejection is therefore often a history of lost balance. Orbits that once coexisted become incompatible, and gravity gradually selects which worlds remain and which are cast away. The expelled planet leaves with whatever mass, composition, and internal heat it already possesses. Ejection changes the orbit, not the planet's basic material identity. A giant world remains a giant world. A rocky world remains rocky. An icy body remains icy. Yet the environmental meaning of those properties changes immediately because the star's steady light and warmth no longer define the outer conditions of existence. At the level of this section, however, the focus remains on the mechanism of removal itself. The important physical reality is that planetary systems can be too crowded, too mobile, or too delicately arranged to keep all their members. Some planets gain safer or tighter places. Others pay for that stability by being scattered outward until the star can no longer hold them. In this unstable gravitational zone, rogue planets are created not by darkness alone, but by competition within young systems. They begin as ordinary members of a stellar family and become solitary because repeated close encounters redistribute motion and energy unevenly. One planet survives inside, another is lost outward. The process is impersonal, governed by gravity rather than intention, and it may unfold long after the first act of formation is complete. The disk has built the worlds. Instability decides whether all of them stay, where masses crowd together and orbits fail to remain compatible. Expulsion becomes one of the natural outcomes. In that sense, a rogue planet born by ejection is the remnant of an internal planetary struggle, a world that leaves not because it was incomplete, but because the system around it could not keep every body in place. Not every solitary planetary mass world needs to begin inside a planetary disk and then be expelled. In some cases, the path may start earlier and farther outward, in the collapsing gas of a star-forming cloud itself. This possibility occupies an uncertain boundary in astronomy, because it concerns objects with planet-like masses that may form in a star-like way. The focus in this section remains entirely within that boundary region. The subject is not ejection from a mature planetary system, but direct formation from a fragment of cloud material that never becomes a star. Here, the rogue planet appears not as a cast-out member of a family, but as a very small outcome of the same general cloud collapse process that produces stars and brown dwarfs. A molecular cloud is a cold concentration of gas and dust in the galaxy, dense enough for gravity to gather matter into new structures. Within such a cloud, some regions become unstable and begin to collapse. As collapse proceeds, the cloud does not always form one single object. It may fragment into smaller clumps, each of which follows its own local path inward under gravity. In the usual picture of star formation, a fragment contains enough material to build a star or at least a brown dwarf. Yet in a complex and turbulent cloud, some fragments may remain much smaller. If one of these condensations gathers only a planetary amount of mass and still contracts as an independent body, the result can resemble a rogue planet in mass even though it never formed around a star. At that point, the distinction between planet and substellar object becomes less straightforward than the word planet usually suggests. Brown dwarfs occupy part of this borderland. They are more massive than giant planets, but not massive enough to sustain the stable hydrogen fusion that powers stars. Their origin is often described more like star formation than like ordinary planet formation. They emerge from cloud collapse rather than gradual assembly in a disk. If the same general process can continue down to still lower masses, then the galaxy may produce free-floating bodies with masses in the planetary range through direct collapse as well. In that case, an isolated object with the mass of a large planet may not have been born as a planet in the common dynamical sense. It may instead be the smallest member of a star formation spectrum, shaped by the fragmentation of a cloud rather than by accretion inside a disk around a star. This is why origin matters so much in classification. If mass alone is used, then a solitary object of a few Jupiter masses may look like a rogue planet whether it formed in a disk or in a cloud fragment. If formation root is used, then the same object might belong conceptually to two different categories depending on its history. The difficulty is that history is hard to observe directly once the object already exists. Astronomers can measure brightness, temperature, motion, and sometimes approximate mass, but they do not usually witness the full birth process of an individual isolated low-mass object. The sky presents the finished body, not the complete record of how it came to be. For this reason, the boundary between very low-mass brown dwarfs and directly formed free-floating planetary mass objects remains partly uncertain. The cloud environment itself encourages this ambiguity. Fragmentation is influenced by density, temperature, turbulence, magnetic fields, and the local balance between pressure and gravity. A denser and colder region can break into multiple collapsing parts more easily under some conditions, while heating from nearby forming stars can suppress the formation of very small fragments. Turbulence can compress gas in one place and disperse it in another. Rotation can alter the geometry of collapse. The result is not a single universal path, but a range of possibilities shaped by local conditions. In that setting, it is plausible that some fragments end up with masses below the usual brown dwarf range. Whether those fragments survive as independent bodies often depends on how efficiently they gather material before their surroundings change. A very small fragment faces a basic problem. Once collapse begins, the forming object does not exist in isolation from the cloud around it. Gas continues to move. Nearby objects may compete for material, and radiation from larger forming stars can heat the environment. A fragment that begins small may accrete more mass and move upward into the brown dwarf regime. Another may be disrupted before it becomes a bound object at all. Only under certain conditions might a fragment remain both independent and low in mass. This is one reason the direct formation route is discussed carefully rather than treated as settled in all cases. Observations indicate that isolated planetary mass objects exist in young regions. It remains uncertain what fraction of them form through direct collapse instead of ejection or other processes. Astronomers look for clues in the properties of these isolated bodies, and in the environments where they are found. A population spread through a very young star-forming region, especially one mixed among low-mass brown dwarfs, may suggest continuity between the two classes. If the number of isolated objects rises smoothly from brown dwarf masses down into the planetary range, that pattern can support the idea that cloud fragmentation extends to very small bodies. On the other hand, if the population appears in ways more consistent with planetary system dynamics, ejection may be the better explanation for some cases. Neither conclusion fully excludes the other. The galaxy may use more than one route to produce similar solitary worlds. In this section, however, the attention remains on the cloud collapse route itself, and the conceptual edge where planets and brown dwarfs begin to overlap. This overlap changes the meaning of the word rogue. In the ejection pathway, the word implies separation from a host star and loss of an original orbit. In the direct collapse pathway, there may never have been a host star to leave. The object is solitary from the beginning. It does not become free-floating after some later event. It is born free-floating, yet because its mass can fall into the same general range as giant planets, and because it travels through interstellar space without a star, it enters the same observational category in many surveys. Astronomers may group such bodies together pragmatically even while their origins remain different. This is not confusion so much as a reflection of nature's habit of producing continua rather than neat boxes. At this boundary, a rogue planet is less a sharply defined type than a meeting point of formation pathways. One path begins in a disk and ends in ejection. Another may begin in a collapsing cloud fragment and never involve a host star at all. Both can yield a dark, solitary body of planetary mass moving through the Milky Way. The difference lies deep in origin, where observation grows difficult and categories lose some of their certainty. In that quiet uncertainty, the edge of the brown dwarf domain becomes one of the most important regions in the study of rogue planets. It is the place where astronomy must ask not only what mass a lonely world has, but what kind of birth the galaxy allows for an object so small and so alone. Among the many uncertain members of the rogue planet population, a single well-measured case has special value because it turns a general idea into a specific physical object. In a field where many detections rely on brief events, faint light, and incomplete information, a solitary world with both estimated mass and estimated distance offers a firmer point of reference. This section remains entirely within that observational ground. The focus is not on the whole galactic census, nor on the processes of birth and ejection in general, but on one measured rogue planet and the methods that allow astronomers to say more than merely that something dark has passed in front of a distant star. Here the subject narrows from population to case, from many possible wanderers to one object whose properties begin to take clearer shape. The object in question is significant because it appears to have a mass comparable to Saturn. That places it below the mass of Jupiter and well within the familiar planetary scale of the solar system. Many isolated low-mass bodies found in young regions carry uncertain masses because those estimates depend strongly on age and cooling models. In this case, the strength comes from a gravitational microlensing event studied with an unusual degree of detail. A background star brightens as the hidden foreground object passes near the line of sight, and the event is observed not by one instrument alone, but through a combination of data from Earth and from space. That combined view allows astronomers to constrain the geometry more effectively than is often possible from a single observing location. This matters because microlensing usually reveals only part of the story. The temporary brightening shows that a lens exists and gives clues to its mass, but some degeneracies remain. A degeneracy in astronomy is a situation in which different combinations of physical properties can produce similar observational signals. A lens can seem to have one mass at one distance, or another mass at a different distance if the event is not measured precisely enough. By observing from more than one location separated by a large baseline, astronomers can detect slight differences in the timing and shape of the brightening. This effect, often called parallax in the microlensing context, helps break the ambiguity. Parallax is the apparent shift in the position or behavior of an object when viewed from different locations. In this case, it refines the lens solution and moves the object from broad suspicion toward a more specific physical description. The measured rogue planet therefore occupies an important observational region between hidden population and direct image. It is still not seen as a resolved globe with clouds, rings, or surface detail. It remains invisible in the ordinary sense. Yet the event yields enough information for astronomers to infer that the lens is a free-floating object with roughly Saturn-like mass at a measurable distance within the galaxy. This is a quieter achievement than a dramatic photograph, but in some ways it is more powerful. A direct image of a very young glowing object can still leave large uncertainty about mass, because age and atmospheric properties matter so much. A microlensing event with a strong geometric solution instead ties the existence of the object more closely to gravity itself. The world is known because its mass shapes space and alters a background beam of starlight. This single case also clarifies the scale of rogue planets for the mind. Discussions of free-floating worlds sometimes drift toward the most massive and easiest examples, especially young objects near the brown dwarf boundary. A Saturn mass rogue planet brings the subject inward toward a more recognizable planetary regime. It suggests that solitary worlds are not limited to the largest giant planets or to ambiguous objects just below the threshold of star-like failure. The Milky Way can contain unbound bodies in a mass range already familiar from the major planets of the solar system. That does not by itself reveal how common such lower mass rogues are, but it demonstrates that at least some of them exist and can be detected with enough care. The galaxy does not hide only massive drifters. It also holds worlds closer to the scale of ordinary giant planets. The method used to measure this object reveals another important truth about rogue planet astronomy. No single technique is sufficient in every case. Ground-based observations provide continuous monitoring of dense star fields and make it possible to discover the event in the first place. Space-based data, gathered from a much more distant vantage point, add the geometric leverage needed to refine the mass and distance. The result is not merely a fortunate detection, but a demonstration of how coordinated observing can strengthen conclusions about isolated dark objects. A rogue planet does not shine helpfully on its own. Knowledge of it must be built from alignment, timing, and the careful combination of signals gathered across very different locations. Even with this improved measurement, limits remain. The event reveals mass and distance more securely than usual, but it does not provide a full biography. It does not tell with certainty whether the object formed in a planetary disk and was ejected, or whether it formed directly from a small cloud fragment. It does not disclose the detailed structure of its atmosphere, the state of any moons, or the long history of its path through the galaxy. A well-measured microlensing rogue planet is still known primarily through gravity and motion, not through the richer direct diagnostics that brighter nearby objects can offer. Yet this limitation does not diminish the importance of the case. In a field where many bodies remain statistical, one physically constrained object becomes a kind of anchor. It proves that the category includes concrete worlds with specific masses, not only abstract inferences from population studies. The Saturn mass rogue planet also stands as a sign of what future surveys may achieve. If one such world can be measured with this degree of confidence through coordinated observations, then a larger sample may eventually reveal how the mass distribution of rogue planets is arranged across the galaxy. Are smaller, isolated planets common or rare? Do giant rogues dominate detection only because they are easier to find? Does the free-floating population extend smoothly downward in mass? This section does not move into those broader questions in detail, because it remains with the single measured case itself. Still, The case quietly carries that weight. It shows that the observational wall is not absolute. A dark planet between the stars can, under the right conditions, be weighed. In this narrowed observational region, one rogue planet takes on unusual importance simply by being measured well enough to stand apart from the surrounding uncertainty. It is not a symbolic wanderer or a speculative class member. It is a particular free-floating world, roughly Saturn in mass, inferred through gravity, distance, and careful geometry. That makes it a stable point in a subject often defined by faintness and ambiguity. The wider population remains difficult, incomplete, and partly hidden. But this one object exists within firmer limits, and because of that, the immense dark inventory of the Milky Way feels slightly less abstract. One lost world becomes a known one, not because it shines, but because gravity briefly makes its passage legible against the light of a distant star. Once a planet has crossed the threshold of escape from its parent star, its motion changes in meaning more than in speed. It does not stop moving when it becomes rogue. It simply ceases to move as a member of one local system and begins to move as an independent body within the larger gravitational structure of the Milky Way. In this section, the focus remains entirely on that solitary passage through interstellar space. The rogue planet is now a traveller between stars, no longer defined by a year around a sun, but by a long galactic drift through the thin matter and deep darkness of the galaxy. Its path is quiet, extended, and usually unnoticed. A planet released from a stellar system carries away the motion it already has and adds to it the energy gained during its final scattering or escape. This means its new path is not random in an absolute sense. It still begins within the broader flow of galactic motion shared by the star from which it came. The parent star itself orbits the center of the Milky Way, and the expelled planet continues as part of that general circulation. Yet the two are no longer bound companions. Their trajectories slowly separate, shaped by their different velocities and by later encounters with the varying gravitational field of the galaxy. The rogue planet, therefore, becomes a solitary object within a larger ordered system, still governed by gravity but no longer attached to a local source of light and heat. The space through which it moves is often called the interstellar medium. This medium is not empty in a strict sense, though it is vastly more tenuous than any atmosphere. It consists of sparse gas, fine dust, magnetic fields, and high-energy particles distributed across the galaxy. A rogue planet passing through it does not feel weather in the ordinary planetary sense. The surrounding matter is far too diffuse for that. Yet this medium still forms the environment of its journey. The planet travels through regions of differing density, through cold clouds and clearer spaces, through spiral arms richer in gas and stars, and through more open stretches where nearby bright objects are scarce. On the scale of the Milky Way, the rogue planet is not passing through nothing. It is passing through the galaxy's thin interior substance. Its motion can endure for immense periods. A rogue planet may remain free-floating for hundreds of millions or billions of years. During that time, the distances it covers are enormous, but the travel is not purposeful or direct in any human sense. It follows a gravitational path, the galaxy's mass distribution, including stars, gas, dark matter, and large structures such as spiral arms, shapes its long course. Some rogue planets likely remain within the broad stellar disk where they originated. Others may be perturbed into somewhat different trajectories over time. Even so, they remain members of the Milky Way unless some exceptionally strong event gives them enough speed to escape the galaxy itself. for most rogue planets. The deep journey is not a departure from the galaxy, but a long drifting residency within it. The loneliness of this motion is real but not absolute. A rogue planet may pass relatively near stars from time to time, though usually not close enough to become captured. The galaxy is crowded on a grand scale and sparse on a local one. That combination defines the nature of interstellar travel. There are many stars in the Milky Way, yet the typical distance between neighbouring stars is so large that direct close encounters remain uncommon. A rogue planet can therefore spend immense spans without any nearby bright companion. When it does pass through a region containing stars, those stars do not usually organise its motion into a stable system. They merely become temporary presences in its sky, bright for a time and then distant again as the planet continues onward. Capture by another star is possible in principle, but thought to be rare under ordinary galactic conditions. For a free-floating planet to become permanently bound to a new star, energy must be removed from the relative motion in a very specific way. This is difficult in a simple two-body encounter. A more complex setting, involving a binary star, a dense stellar environment, or some other mechanism for energy exchange, may improve the chance, but such events are not expected to define the usual fate of rogue planets. The more common outcome is continued freedom. The rogue planet passes through the galaxy without settling easily into a new household. Its defining condition remains persistence in isolation rather than frequent reattachment. This long drift also changes how the planet is detected, or more often not detected. In interstellar space, far from a host star and often long after its initial warmth has faded, it becomes one of the most difficult kinds of object to observe. It emits little light, reflects almost none that can be usefully seen at great distance, and occupies no regular orbit that would repeatedly announce its presence. Detection therefore depends on special circumstances, such as youth, residual heat, or a chance micro-lensing alignment with a background star. The ordinary state of a rogue planet during its galactic passage is observational silence. It exists physically and dynamically, but to distant observers it usually remains hidden unless gravity or faint infrared emission briefly reveals it. Its path is also shaped by time in another way. The longer the journey continues, the less obvious its origin becomes. A recently ejected planet in a young region may still be associated loosely with its birth environment by motion or location. After long ages of galactic drift, that connection becomes harder to reconstruct. The planet may cross many regions, experience small perturbations, and lose any clear observational link to the star or system from which it came. In this sense, interstellar passage erases biography. The world remains itself, but its history becomes more difficult to read. Motion through the Milky Way does not only relocate the object, it also hides the evidence of where the journey began. At this stage, the rogue planet is best understood as a planetary body whose primary environment is no longer a star system, but the galaxy itself. Gravity still rules its movement, but the relevant frame has widened. The star that once defined local order no longer does so. Instead, there is galactic rotation, diffuse interstellar matter, rare encounters, and prolonged darkness punctuated only occasionally by the presence of nearer stars. This is the physical reality of interstellar drift. It is not dramatic in every moment, but it is profound in scale and duration. A rogue planet travelling this way is not falling aimlessly through empty blackness. It is moving as a free world within the Milky Way, carrying its mass, structure, and internal history through an environment too thin to stop it, and too vast to make its passage easy to witness. The galaxy becomes its only enduring system. The parent star is gone from practical importance, and no replacement usually appears. What remains is solitary motion through interstellar space, sustained by inertia, guided by gravity, and hidden for most of its existence from every distant eye. After the long interstellar drift becomes the normal condition, the next region lies at the exposed boundary where a rogue planet meets space. This is the outer energy balance of a starless world, the thin interface at which heat leaves the planet and almost no useful warmth comes in. In an ordinary planetary system, a star dominates this balance. Sunlight arrives continuously, warms the outer layers, and sets the thermal character of the surface or cloud tops. A rogue planet does not live under that rule. Once it has no host star, the surrounding darkness is not only visual, it is energetic. The world receives extremely little external radiation compared with a planet orbiting near a sun. Its outer condition is governed mainly by loss rather than gain, by what the planet can still retain and slowly release from within. Space is often imagined as simply cold, but in physical terms the important fact is that space provides almost no incoming heat to compensate for what a planet radiates away. Every object warmer than its surroundings emits thermal radiation. A rogue planet does the same. Its exposed outer layers send energy outward in the form of infrared light, gradually cooling the body over time. The background into which this radiation escapes is extraordinarily dark in thermal terms. There is faint radiation left from the early universe, now cooled to only a few degrees above absolute zero, and there is scattered light from distant stars and the diffuse glow of the galaxy. Yet for a rogue planet these inputs are feeble. They do not replace the strong, steady heating that a nearby star would provide. The planet therefore lives in a state of persistent net energy loss. This net loss defines the meaning of starlessness at the outer boundary. A rogue planet may still pass through regions where stars appear in its sky, even then, unless it becomes bound in a new system. Such encounters usually do little to change the basic energy balance. The light from distant or passing stars remains weak compared with the direct radiative input that ordinary planets receive from a host sun. At its outer skin, the rogue planet feels the galaxy mostly as a lack of warmth. The open dark allows energy to escape far more effectively than the external sources replace it. What keeps such a world from becoming immediately as cold as the surrounding void is its own stored and ongoing internal heat. A young, giant world retains heat from its formation. When matter falls together and gravitational energy is converted into thermal energy, large gaseous bodies can also continue to warm themselves internally through slow contraction, because compression releases energy as the planet gradually settles. Rocky and icy worlds may retain heat left from accretion and differentiation. Differentiation is the separation of materials by density, with heavier substances tending inward and lighter materials remaining above. Smaller solid worlds may also draw modest long-term warmth from radioactive decay within their interiors. At the outer boundary, these sources matter only because they feed a slow, outward flow of heat. For this reason, the exposed top of a rogue planet is best understood as a cooling surface rather than a sunlit one. It is the place where internal energy finally escapes after moving outward from deeper layers. On a giant rogue planet, there may be no solid ground at that upper boundary, only the top of a deep gaseous envelope. On a rocky or icy rogue, the boundary may indeed be a solid surface. In either case, the physical role is similar. The outermost layer mediates between internal warmth below and near empty space above. If the planet is young or massive, that boundary may still emit measurable infrared radiation. If the planet is old and small, the emitted energy may be far weaker. Age is one of the clearest controls on the outer energy balance. A newly formed or newly ejected rogue planet begins its isolated existence with a larger reservoir of heat. Over time, as radiation carries energy away, the planet cools and the outward flux declines. Flux is the rate at which energy passes through a given area. For the rogue planet, the outer flux falls gradually as the body ages and internal reserves diminish. Massive bodies hold heat longer. Giant planets with thick envelopes cool differently from smaller rocky objects. Composition matters, size matters, and the efficiency with which heat travels outward matters. Yet the general direction remains the same. Without starlight to dominate the outer temperature, the top of the world increasingly reflects the slow exhaustion of internal energy. Even in deep isolation, the outer boundary does not become completely featureless in thermal terms. Temperature differences may persist across place and time, depending on rotation, lingering internal activity, cloud cover in gaseous worlds, or the properties of frozen material on solid ones. But these differences occur within a regime defined by low external input. On an ordinary planet, the main contrast may be between day and night under stellar illumination. On a rogue planet, that familiar control loses much of its power. The central fact is not alternating sunlight, but the absence of sunlight. The exposed layer must respond chiefly to internal heat leaking upward and to radiation carrying that heat away into space. This makes rogue planets unusual laboratories for planetary cooling. In a bound system, the outer temperature of a planet often records a mixture of starlight, reflection, atmospheric dynamics, internal heat, and orbital geometry. In a rogue world, that mixture is stripped down. There is little incoming power to blur the role of internal warmth. What remains is a clearer contest between stored heat and radiative loss. That simplicity helps astronomers think about what such a world might still emit, especially if it is young enough or large enough to remain detectable in infrared light. In this outer region, a rogue planet is therefore neither truly dead nor actively warmed from beyond. It is a body that continues to cool under open cosmic conditions, shedding the remnants of formation and the products of slow internal processes into surrounding darkness. Its exposed outer layer records that condition directly. It is the place where the absence of a star is expressed as a persistent thermal deficit. The world still has warmth, sometimes more than intuition would expect, but that warmth is self-supplied and steadily diminishing. In the long quiet of interstellar space, the outer skin of the rogue planet serves as the final ledger of this exchange, losing energy to the galaxy while receiving almost nothing in return. Above the deeper body of a rogue planet lies a more delicate region, the high atmosphere, where pressure is low, matter is thin, and the planet's faint escaping heat becomes legible to distant instruments. This is the next inward layer after the exposed outer energy balance, but it remains very near the top of the world. In a young rogue planet, this upper atmosphere is especially important because it is one of the first places where astronomers can read physical information from the weak infrared light the planet emits. The planet still has no star to light it from outside in any dominant way. Instead, the upper air is shaped mainly by the slow, upward movement of internal heat, and by the outward loss of that energy to space. In this region, the atmosphere is not yet dense enough to trap heat strongly, or to form the deeper weather structures that belong to lower layers. It is a thinner, more transparent zone where temperature, molecules, and gravity leave subtle marks in the escaping light. The upper atmosphere of a rogue planet differs from that of a planet strongly irradiated by a nearby star. In an ordinary hot exoplanet close to its star, the high atmosphere may be heavily influenced by intense incoming radiation. Ultraviolet light can alter chemistry, heat specific layers, and drive strong departures from deeper equilibrium. A rogue planet usually lacks that dominant external forcing. Even if starlight from the galaxy and the general radiation field of space are not literally absent, they're too weak to define the upper atmosphere in the way a host star defines the atmosphere of a bound planet. The result is a different thermal structure. The upper air of a rogue planet is governed more by internal cooling than by absorbed sunlight. This gives the layer a quieter and more self-contained physical character. Pressure in this region is low enough that particles are widely spaced compared with deeper atmospheric layers. Collisions still occur, but the air is thin, and the way radiation moves through it becomes especially important. Some wavelengths of infrared light pass outward more easily, while others are absorbed and re-emitted by molecules present in the gas. This selective interaction gives the upper atmosphere one of its main observational roles. It acts as a filtering layer. The light escaping from below does not emerge unchanged. It carries the imprint of the gases through which it passes. When astronomers divide that light into its component wavelengths, they obtain a spectrum. A spectrum is a spread of light by wavelength that reveals how matter absorbs or emits energy. In the faint spectrum of a young rogue planet, the upper atmosphere leaves clues about temperature and composition. Among the most important molecules in this regime are water vapor, methane, and in some cases carbon monoxide. Their presence depends on temperature, pressure, and the broad chemical balance of the atmosphere. Water is common in many hydrogen-rich planetary atmospheres at suitable temperatures, and methane becomes especially important in cooler objects. These molecules do not announce themselves as visible colors. Instead, they produce absorption features in infrared light, narrow or broad regions where radiation is reduced because specific molecular motions interact with specific wavelengths. When such features are detected, astronomers can infer that these gases are present in the upper layers through which the light has traveled. The interpretation is careful rather than absolute, because cloudiness, gravity, and temperature structure can complicate the signal. Even so, the upper atmosphere often provides the first accessible evidence that a rogue planet is not merely a warm mass, but a world with a real gaseous envelope and identifiable molecular content. Temperature in the high atmosphere is usually lower than in the deeper layers below, but it is not determined by external cold alone. Heat still rises from the interior and from low atmospheric regions, and the upper air adjusts to the balance between that upward energy flow and the radiation escaping outward. Because the atmosphere is thin here, small changes in composition or structure can affect how efficiently different wavelengths leave the planet. This is why the upper atmosphere matters so much to observation. It is not simply a passive lid. It is the layer where the outgoing light is most directly shaped before entering interstellar space. In a young rogue planet, which still emits enough infrared radiation to be measured, this shaping effect makes the upper atmosphere a readable boundary between hidden interior energy and the observing telescope. Surface gravity also leaves a signature in this region. Gravity controls how tightly the atmosphere is held and how quickly pressure changes with altitude. A lower gravity object tends to have a more extended atmosphere, while a higher gravity object compresses its gaseous layers more strongly. In practice, This can influence the appearance of spectral features and help astronomers distinguish a young, low-mass rogue planet from an older or more compact brown dwarf. Youth often means lower surface gravity because the object is still relatively puffed up from its recent formation and has not fully contracted. As a result, the upper atmosphere of a young rogue planet may show signs consistent with a softer vertical structure than that of an older, denser object. This does not make classification easy, but it provides another reason why the upper air is scientifically valuable. It carries information not only about molecule and temperature, but also about the broader physical state of the world. Because the planet has no nearby sun, the high atmosphere also experiences a different radiative environment from that of many familiar planets. Strong dayside heating, star-facing circulation patterns, and photochemical forcing driven by intense stellar light are much less important here. The upper atmosphere is therefore often closer to a state controlled by the planet's own thermal emission. This does not mean it is perfectly simple. Real atmospheres remain dynamic, and chemistry can still evolve without strong stellar irradiation. But the absence of a dominant external energy source removes one of the major complications seen in many bound exoplanets. For astronomers, this can make young rogue planets useful objects for studying atmospheres shaped more directly by internal planetary conditions. In this high atmospheric layer, observation and physics meet in a particularly clear way. The gas is thin enough to let infrared light emerge, yet present enough to mark that light with evidence of molecules, temperature, and gravity. The atmosphere is not deep enough here to reveal everything about the planet below, but it is transparent enough to offer a first reliable reading of what kind of world the rogue planet may be. Astronomers do not see a bright globe hanging in space. They receive a faint spectral signal from a dim object and learn from the pattern carried by the upper air. This is the scientific meaning of the upper atmosphere of a young rogue planet. It is the planet's readable edge, a thin region where internal heat becomes observable, where water and methane may disclose themselves, and where low pressure allows the faint infrared identity of the world to escape into the dark. It remains a high and delicate layer, still near the top of the planet, but it holds far more information than its thinness suggests. In the absence of starlight, the upper atmosphere becomes one of the quietest and most revealing places a rogue planet possesses. Below the thin high atmosphere lies a thicker and more complex middle region, where a rogue planet's air begins to gather structure. Here the gas is still part of the open outer atmosphere, but pressure is greater. Temperatures are more moderate than in the highest layers, and matter no longer behaves as a nearly transparent veil alone. In this region, clouds can form, hazes can persist, chemistry can shift from place to place, and the faint light leaving the planet acquires a more textured character. The subject remains fully within the atmosphere and does not descend yet into the deepest pressure-dominated zones. It stays with the middle layers, where suspended particles and moving gases shape much of what a young giant rogue planet looks like in infrared light. A cloud in a planetary atmosphere is a region where material condenses into tiny droplets or solid grains suspended in the air. On Earth, clouds form mainly from water. On giant rogue planets, especially those still warm from youth, the range of cloud materials can be very different. In sufficiently warm atmospheres, silicate particles may condense, and iron-bearing materials may also form cloud layers. These substances do not float as familiar shining metals or stones. They exist as tiny grains, mix through the gas, distributed across levels where temperature and pressure allow them to remain suspended. In somewhat cooler conditions, other compounds may condense instead. The result is an atmosphere where cloud composition depends strongly on temperature, and temperature in turn depends on age, mass, and the lingering heat of the planet itself. This middle atmospheric zone is especially important because clouds do not merely occupy space. They alter the way the planet emits and absorbs radiation. A clear atmosphere lets some wavelengths of infrared light escape more easily from below. A cloudy atmosphere blocks, scatters, or reshapes that outward flow. If cloud particles are abundant, they can flatten or mute spectral features that would otherwise appear more strongly. They can also change the apparent brightness of the planet at different wavelengths, for observers far away. This means the middle atmosphere can hide as much as it reveals. A rogue planet may be warm enough to emit measurable radiation, but the cloud layers through which that radiation passes may soften the clear signatures of gases beneath or above them. The cloud structure is not necessarily smooth or uniform around the whole planet. Atmospheric circulation can produce patchiness. With thicker clouds in some regions and thinner openings in others, rotation can then carry these regions into and out of view. As a result, the brightness of a rogue planet may vary slightly with time. This variability is one of the most informative signs of middle atmospheric activity. It suggests that the atmosphere is not static, even in the absence of a nearby star. The planet's own internal heat drives motion, convection, and the rising and sinking of gases. Convection is the transport of heat by the movement of material itself, with warmer gas tending to rise and cooler gas tending to sink. In a giant rogue planet, convection from below can feed energy into the middle atmosphere and help maintain cloud patterns that shift over time. Hazes may also appear in this region. A haze is made of very small suspended particles, often finer than typical cloud droplets or grains, spread through an atmospheric layer in a more diffuse way. On a rogue planet, hazes may arise from chemical pathways in which molecules combine into more complex particles, or from vertical transport that keeps fine material aloft. Because the planet lacks strong stellar ultraviolet radiation, the exact balance of haze production may differ from that seen in strongly irradiated atmospheres. Even so, hazes can still influence the outgoing light by scattering and absorbing radiation in subtle ways. They may soften contrast, redden the emitted spectrum, or contribute to the muted appearance of certain spectral features. In practice, hazes and clouds often become intertwined in interpretation, since both complicate the reading of the planet's emitted light. Chemistry in the middle atmosphere is shaped by both equilibrium and motion. Chemical equilibrium is the state expected if temperature and pressure alone determine which molecules dominate. In a warm, hydrogen-rich atmosphere, carbon may favor carbon monoxide at certain depths and temperatures, while methane becomes more stable in cooler regions. Water remains important across a broad range of conditions. Yet real atmospheres do not stay motionless long enough for simple equilibrium to describe every layer completely. Vertical mixing can carry gases upward from warmer regions or downward from cooler ones, preserving molecules in places where they would not dominate if the air were perfectly still. This means the middle atmosphere often records a dialogue between chemistry and circulation. The observed spectrum then reflects not only temperature, but the planet's moving internal weather. Because rogue planets are not strongly irradiated from outside, the middle atmosphere is governed largely by internal processes. The heat rising from below helps set the temperature profile, and the resulting circulation may be broader and more vertically connected than in some planets dominated by star-facing heating. There is no permanent day side being baked under close stellar light, and no permanent night side defined by sudden absence of that light. Instead, the energy source is distributed from within. That does not eliminate atmospheric variety, but it gives the middle atmosphere a different character. Its motions and cloud patterns arise more from internal heat transport and rotation than from direct stellar forcing, observationally. This layer is one of the main reasons young rogue planets can appear difficult to classify cleanly. Clouds can make a lower mass object resemble a higher mass one in some wavelength ranges, or make a younger atmosphere resemble an older one if the cloud thickness changes the emitted spectrum in the right way. Low gravity, youth, and cloudiness often act together. A younger object tends to have a more extended atmosphere, and that atmospheric structure may help keep cloud particles suspended differently from what happens in an older, denser body. The middle atmosphere therefore becomes a place where age, gravity, and chemistry all meet. Astronomers trying to interpret the light of a rogue planet must account for all three. This region also reminds astronomy that a rogue planet is not a bare cooling sphere with a simple smooth shell. Even without a star, it can possess active atmospheric structure. Its clouds may gather and thin, its hazes may soften the escaping light, and its chemistry may be continually adjusted by motion from below. The middle atmosphere is not the deepest source of the heat, but it is the place where that heat first becomes meteorology in a recognizable sense. It is where thermal energy turns into circulation, suspended particles, and changing patterns in brightness. In these layers, the rogue planet begins to look like a genuine weather world rather than merely a dim, isolated mass. The weather is not Earth-like, and the clouds are not made of ordinary water alone, but the principle is familiar enough. Gases move, temperatures differ, particles condense, and light is shaped by what hangs in the air. The middle atmosphere thus becomes one of the richest regions of the rogue planet's outer body. It is where cloud decks, hazes, and chemistry turn faint infrared emission into something more complex, carrying the signs of motion, suspended matter, and active atmospheric life within the long darkness between the stars. Beneath the cloud-rich middle atmosphere lies a deeper region where the air grows heavier, pressure rises steadily, and the planet's heat is retained with increasing efficiency. This is not yet the solid or liquid interior of the world. It remains part of the atmosphere, but it is an atmosphere transformed by weight. In these lower layers, gas is compressed by the enormous mass above it, and the physical character of the planet changes from a place of drifting particles and visible spectral features into a denser thermal reservoir. The subject in this section remains entirely within that deep air. It does not descend to any buried core or hidden ocean. It stays with the lower atmospheric envelope, where cooling slows because the planet's own gases begin to act as a thick insulating blanket around the heat below. Pressure is one of the defining conditions here. Pressure is the force exerted by material pressing inward or downward on what lies beneath it. In a deep planetary atmosphere, each layer supports the weight of the layers above. As depth increases, that burden becomes greater, and the gas is squeezed into a denser state. Molecules move in less open space, collisions become more frequent, and the transport of heat changes character. A rogue planet, especially a giant one, may possess an atmosphere so deep that the distinction between atmosphere and bulk body becomes less obvious than it is on a rocky planet. There is no simple boundary like the surface of Earth. Instead, there is a gradual descent into thicker and hotter gas, with pressure and density increasing continuously. This deeper air matters because it governs how efficiently internal heat can escape. Heat produced or retained within the planet does not leap directly into space. It must pass upward through layer after layer of gas. In the deep atmosphere, the gas itself absorbs and re-emits thermal radiation many times, slowing the outward flow. This is the essential meaning of atmospheric insulation. The atmosphere does not create energy from nothing, it delays its loss. The thicker and more opaque the lower atmosphere becomes to infrared radiation, the more gradually the planet cools. For a rogue planet without stellar heating, this inward retaining effect is especially important. It helps determine how long the world can remain warmer than the surrounding dark by holding back the release of its own internal energy. Opacity is a useful term here. It refers to how strongly matter blocks or absorbs radiation passing through it. A deep atmosphere with high opacity at infrared wavelengths does not let heat escape easily in the form of radiation alone. As a result, heat may be transported upward by convection through part of the lower envelope. Convection becomes important when warm material from below rises and cooler material from above sinks, carrying energy through bulk motion rather than only through radiative transfer. In many giant planets, the deep atmosphere is expected to be largely convective because the interior heat flow is strong enough and the overlying gas opaque enough that rising and sinking motions become an efficient transport mechanism. The deeper air of a rogue planet is therefore not necessarily still. It may be part of a slow but persistent overturning driven by the release of heat from within. As gas descends under increasing pressure, temperature also rises. This rise does not come from nearby sunlight. It arises because deeper layers sit closer to internal heat and because compressed gas tends to warm. The result is a temperature gradient, a gradual change in temperature with depth. If the gradient becomes steep enough, convection is favored, and the lower atmosphere may circulate energy upward in broad vertical motions. In that sense, the deep air acts as a mediator between the hidden thermal interior and the thinner atmospheric regions above. The middle atmosphere may hold clouds and changing weather, but the deep atmosphere supplies much of the energy that makes such activity possible. It is the reservoir below the visible atmospheric drama, storing and transmitting the planet's remaining warmth. Chemical conditions also shift in this region. At greater pressure and temperature, the balance between molecules changes. Some species that dominate higher, cooler layers become less stable, while others become more favored. Carbon chemistry is one example. In cooler upper layers, methane may be prominent, while deeper and hotter conditions can favor carbon monoxide more strongly. Water remains important, but its behavior and abundance by altitude depend on both chemistry and condensation. In very deep layers where temperatures rise sufficiently, condensed particles that form clouds higher up may no longer remain condensed at all. Materials return to gaseous form, and the atmosphere becomes chemically simpler in one sense and more extreme in another. The deep air is therefore not a place of delicate spectral tracery as much as a domain of hot compressed gas, whose composition reflects high-pressure equilibrium more closely than the upper layers do. The slow cooling of a rogue planet depends intimately on these deep conditions. A giant free-floating world may spend vast spans radiating away the heat of formation, contraction, and internal processes, but the pace of that cooling is not set only by the amount of stored energy. It is also set by how difficult the deep atmosphere makes the escape of that energy. A thicker envelope, higher mass, and greater opacity all tend to prolong the cooling history. This is why two rogue planets of different mass or composition may age thermally in very different ways. One may dim relatively quickly, another may remain measurably warm for a much longer interval. The deeper atmosphere shapes that difference by controlling the efficiency of heat loss over long times. In the case of lower mass or more solid rogue planets, the deep atmosphere may be thinner or absent compared with the giant world, but where a substantial atmosphere does exist, the same principle holds. Pressure rises downward, heat is retained more effectively below, and the atmosphere acts as part of the thermal system rather than as a superficial skin alone. For a giant rogue planet, this effect becomes especially powerful because the atmospheric envelope is not a minor outer feature. It is a large fraction of the planet itself. The cooling history is therefore inseparable from the physics of deep gas under pressure. This region also marks a transition in observational reach. The higher atmosphere can leave readable signs in the light that escapes to distant telescopes. But the deep atmosphere is much harder to probe directly. Its properties are inferred through models, through the planet's overall brightness, through the structure of the spectrum, and through comparison with similar objects. The lower one goes in this gaseous envelope. The more completely it withdraws from direct view. Yet although hidden, it remains essential. The deep air determines how much warmth the rogue planet still has available to show at all. In this lower atmospheric zone, the rogue planet becomes a world of retained heat and growing compression. The air is no longer thin or easily read. It is heavy, opaque, and thermally powerful. It stores, delays, and redistributes energy, making the difference between rapid fading and long endurance. The middle atmosphere above may shift with clouds and chemistry, but the deeper air beneath it governs the slower rhythm that underlies them all. It is the insulating depth through which internal warmth must struggle upward, and because of that struggle, a rogue planet can remain a warm body in a cold galaxy for far longer than simple darkness might first suggest. Not every rogue planet is a giant world wrapped in a vast deep atmosphere. Some are likely smaller bodies made mainly of rock, ice, or a mixture of both. In such worlds, the next inward region after the open boundary with space is not a thick gaseous envelope but a solid outer shell. This shell is the frozen crust, the uppermost rigid layer directly exposed to the darkness between stars. In a starless environment, that outer surface would lose heat steadily and receive almost no useful warmth from outside. Over long spans, the top of the world would become intensely cold. Any water at the immediate surface would freeze. Many volatile substances, meaning materials that can easily change between gas and solid under planetary conditions, would also tend to condense or remain locked as ice if the temperature were low enough. The result is an outer shell shaped above all by freezing. At the surface of such a rogue planet, the absence of stellar light changes the physical landscape completely. There's no regular dayside heating, no seasonal warming from a host star, and no direct solar energy driving a familiar surface cycle. The ground or ice at the top is governed by radiative loss to space and by the slow upward seepage of heat from below. Because the external thermal input is so weak, the uppermost materials settle toward very low temperatures. Ice, if present, becomes hard and stable. Rocks, if exposed, would also cool deeply, though their behavior differs from that of volatile materials. A surface made of mixed rock and ice might develop a rigid frozen layer over nearly everything that can solidify. The planet's outer face would therefore be quiet, dark, and thermally severe, more a preserved boundary than an active sunlit surface. This frozen crust can take different forms depending on the planet's size. composition, and any atmosphere it may retain. A bare, rocky rogue planet with very little air would cool efficiently at the top and develop a cold, rigid exterior directly open to space. An icy rogue planet, or one with large amounts of water and other frozen materials near the outside, may build a thicker cryosphere. A cryosphere is the portion of a world where water and similar substances remain frozen. On a rogue planet, this frozen domain may extend from the surface down through a substantial shell. If the world retains even a modest atmosphere, that atmosphere may slightly reduce heat loss compared with a perfectly bare surface, but unless the atmospheric blanket is strong, the surface itself is still expected to remain extremely cold. In all cases, the topmost region records the same governing fact. External darkness favours freezing. The frozen shell is not necessarily thin. Ice is a good insulator compared with open exposure to space, and once a thick layer forms, it can slow the loss of heat from deeper levels. This creates an important contrast between the outermost meters or kilometers and the material farther below. The top remains strongly coupled to the cold of space, while lower levels feel that cold more gradually. Over time, the crust becomes a barrier as much as a surface. It is the rigid roof under which deeper materials may follow a different thermal history. This does not mean every rogue planet keeps warmth beneath its frozen exterior. The outcome depends on size, composition, and heat available from within. But the physics of a thick icy shell does allow the possibility that the surface can be far colder than what lies below. Water is central to this possibility because it changes phase in ways that strongly affect planetary structure. At the top, low temperature drives water into ice. Deeper down, pressure rises and heat from within becomes more important, if those deeper conditions cross the relevant melting boundary. Liquid water may exist beneath the frozen shell even while the surface remains entirely solid. In planetary science, such a configuration is called a subsurface ocean. It is an ocean buried under an ice layer rather than exposed to open air. In the case of rogue planets, this idea is treated carefully. There is no confirmed detection of a subsurface ocean within a free-floating planet. Yet physical models indicate that, under some conditions, buried liquid water is possible if internal heat and insulation are sufficient to prevent the entire water inventory from freezing solid. The required heat does not need to be large by stellar standards. It only needs to be persistent enough and trapped well enough to maintain melting conditions below the crust. The insulating effect of ice matters because it slows the escape of that heat. Pressure matters because it changes the behavior of water and the temperature conditions for liquid stability. Planetary size matters because a larger body tends to lose internal heat more slowly than a smaller one. Composition matters because salts, ammonia, and other materials mixed with water can lower the freezing point and broaden the range of conditions under which liquid layers might survive. These are not guarantees. They are the reasons why buried water remains physically plausible in some rogue planets, despite the intense cold at the surface. If such a subsurface liquid layer exists, it would not resemble an open terrestrial ocean under a sky. It would be sealed away under darkness and ice, with no contact with sunlight. Its upper boundary would be the underside of the frozen shell. Its lower boundary would be warmer material beneath. Perhaps additional ice phases under greater pressure or rocky material, if the water layer rests over a solid interior. The liquid would be hidden from direct view, and its persistence would depend on long-term balance rather than surface weather. In this section, the main importance of buried water is structural. It marks a transition from the rigid frozen exterior to a less rigid layer below, showing that a rogue planet's outer body may be more internally diverse than its silent surface suggests. The presence or absence of such buried water remains uncertain for real rogue planets, because these worlds are extremely difficult to observe in detail. For small and cold, free-floating planets, direct data are sparse. Much of the discussion comes from well-grounded theoretical modelling based on planetary heat flow, ice physics, and the known properties of water under pressure. These models do not establish that most rogue planets have hidden oceans. They indicate that some could, especially if they are sufficiently large, water-rich, and thermally insulated. A smaller or drier rogue planet may instead freeze more completely, forming a thick, rigid shell with little or no liquid beneath. The outer crust therefore does not have one universal form across all rogue worlds. It spans a range from bare frozen ground to deep global ice shells that may conceal liquid layers below. What unites these cases is the role of the crust as the outermost solid region of planetary survival in darkness. It is the layer that faces space, accepts the full consequence of lost starlight, and hardens accordingly. It also determines how strongly the interior is isolated from that external cold. A thin crust allows heat to escape more readily. A thick, icy shell slows that escape, and can preserve warmer conditions underneath for longer times. In this way, the frozen outer region does more than record the planet's exposure to interstellar space. It actively shapes the thermal fate of what lies beneath it. This surface and near subsurface region therefore completes the outer solid body of the rogue planet. Above it is darkness and weak radiation. At it, water and volatiles freeze into a rigid exterior. Beneath it, conditions may become less severe, and in some cases liquid water may remain trapped below the ice. The crust is silent, cold, and often hidden from observation, yet it is one of the most consequential layers a small rogue planet can possess. It is the boundary where interstellar cold becomes geology, and where a world that appears completely frozen from outside may still keep a different state concealed below its hard, dark shell. Below every crust, buried ocean, or deep atmosphere lies the final inward region of a rogue planet, the interior where its deepest thermal history and structural identity are held. This is the domain of mantle, core, compression, and long-term heat. It is also the region least accessible to direct observation, and yet most responsible for determining how long a solitary world remains geologically or thermally alive. In this section, the focus stays entirely within that hidden interior. The rogue planet is no longer treated as a drifting body in the galaxy or as a surface facing darkness. It is treated as a layered mass whose deepest materials continue to shape its fate long after the loss of any parent star. Here, the central questions concern internal heat, differentiation, and the endurance of hidden activity in isolation. A planet does not begin as a perfectly ordered object. During formation, matter gathers through impacts, compression, and gradual accumulation. These processes generate heat. As the young body grows, heavy materials such as iron tend to sink inward while lighter silicates, ices, or gases remain above. This process is called differentiation. It is one of the most important internal transitions in planetary evolution because it creates distinct layers with different densities and compositions. A differentiated rogue planet may have a metallic core, a rocky mantle, and, depending on its nature, outer layers of ice, liquid, or gas. Even if the planet later becomes starless and cold at the surface, the internal arrangement established during its early history can remain for immense spans. the outer darkness does not erase the structural consequences of its formation. The deepest source of enduring warmth is not the absence of cooling, but the persistence of eternal energy. Some of that energy comes from the planet's birth, when impacts and compression heated the growing body. Some may come from contraction, especially in giant planets, where slow inward settling under gravity continues to release energy over long times. In rocky interiors, radioactive decay can provide another long-lived contribution. Radioactive decay is the gradual transformation of unstable atomic nuclei into more stable forms, releasing energy as heat. On Earth and other rocky bodies, this process is an important part of internal thermal history. In a rogue planet with a substantial rocky component, it can continue for billions of years, though at a declining rate as radioactive materials are used up. The importance of this source depends on the planet's composition and mass, but where it is present, it adds to the hidden warmth that resists complete interior freezing. How long a rogue planet retains this heat depends on size more than on almost any other single factor. Large bodies cool slowly because heat must travel a longer path outward, while the volume storing that heat grows faster than the surface area losing it. Small bodies cool more quickly because they have less internal energy relative to the area through which that energy can escape. This simple geometrical truth has profound consequences. A giant rogue planet can remain internally warm for a very long time, even while its outer layers darken and cool. A smaller rocky rogue may lose heat more rapidly, but even there the interior does not necessarily become inert at once. Insulating layers, whether thick atmosphere, deep ice, or both, can prolong the retention of warmth below. The deepest region of the planet therefore lives on a different clock from the surface. In rocky or mixed composition rogue planets, the mantle becomes the main reservoir and conveyor of internal heat above the core. The mantle is the thick layer of rock between crust and core, capable over long times of very slow flow, even though it behaves rigidly on short timescales. If the mantle remains warm enough, convection can occur there as well as in the atmosphere. Mantle convection is the slow transport of heat by the movement of solid but deformable rock. With warmer material rising and cooler material sinking over vast spans of time, this process can help drive long-term geological activity. Whether a rogue planet experiences anything like plate tectonics is far less certain, and likely depends on many factors, including size, composition, water content, and crustal strength. Observations do not currently allow firm conclusions on this point for rogue planets. What can be said is that an internally warm mantle gives the planet a mechanism for redistributing heat long after surface freezing has taken hold. The core, if metallic and at least partly fluid, introduces another possibility. A moving electrically conducting fluid can generate a magnetic field through dynamo action. A dynamo is a process in which motion within a conductive liquid produces and sustains planetary magnetism. In the solar system, such magnetic fields exist in several worlds and reflect hidden internal motion. For rogue planets, the existence and persistence of a magnetic field remain uncertain because they depend on internal structure, cooling rate, composition, and the state of the core. A giant planet may generate a strong magnetic field through internal conductive layers, while a smaller rocky rogue might generate one only if its core remains partly molten and convecting. This magnetic possibility is important not because it can be observed easily in most rogue planets, but because it signals that the deepest interior may remain dynamic rather than dormant. Magnetism, where present, would be one more sign that isolation in darkness does not immediately mean internal death. The deepest interior also shapes the possibility of long-lasting habitable niches in a narrow and highly qualified sense. Habitability here does not mean an Earth-like surface under sunlight. It means only that some internal configuration might preserve liquid water or chemically active environments below an ice shell for very long times. If a rocky core, warm mantle, and insulating outer layers work together effectively, then the buried interior could remain more active than the silent exterior suggests. This possibility is physically plausible in some models, especially for worlds with abundant water and adequate heat retention. It remains uncertain how common such cases are among real rogue planets. The hidden interior is therefore the place where the most restrained form of lasting potential survives, not as open biosphere or surface climate, but as protected internal warmth. For giant rogue planets, the deepest interior may look very different from that of rocky worlds. The central region could involve compressed fluid layers, perhaps surrounding a denser core of heavy elements, all under pressures far beyond familiar planetary conditions. In these worlds, the word core still refers to the deepest differentiated region, but the surrounding material may not resemble a terrestrial mantle at all. Even so, the same basic principle applies. Internal heat, compression, and slow release determine the long life of the body. The details differ, yet the deepest region remains the engine of persistence. At this final inward level, a rogue planet becomes most itself. Surface conditions may resemble those of many cold isolated bodies, and atmospheric appearance may change with age and composition, but the deepest interior carries the unique thermal memory of formation, composition, and size. It governs whether the planet cools quickly or slowly, whether buried water might remain liquid, whether geological motion can continue, and whether magnetic activity is possible. The center of the rogue planet is therefore not a dead endpoint, but the last and most enduring source of change within the whole world. In complete isolation from any star, the deep interior continues its work unseen. Heat moves outward slowly, layers remain separated by density, and the core preserves the longest memory of the planet's beginning. The galaxy may know the rogue planet only as a dim drifting mass, but at its center the world can remain complex for ages beyond the freezing of its surface. This innermost region is where the lost world stops looking lost and begins to look self-sustaining in the only way available to it, not through external light, but through the stubborn endurance of its own hidden warmth. In the end, the rogue planet moves on without witness. It carries no sunrise, no returning season, no fixed sky arranged by a nearby star. Around it there is only the wide structure of the galaxy, faint radiation, scattered matter, and the long quiet of interstellar distance. Yet the world is not empty of process. It continues to radiate what warmth it still holds. Its atmosphere, if it has one, continues to rise and settle. Its frozen shell, if one lies at the surface, continues to guard whatever deeper layers remain less cold. Far below, heat continues to travel outward at its own slow pace, as it does in every world that has not entirely surrendered its beginning. This makes the rogue planet a different kind of planet, but not a lesser one. It is not organized by daylight, but by endurance. It does not depend on constant illumination to remain a real world with structure, chemistry, and time written into its layers. Even in darkness, matter keeps its order, gravity keeps its hold, ice remains ice, gas remains in motion, stone keeps the memory of heat, and the deepest core preserves the last quiet force of planetary history. The lost world is still a world. Within the Milky Way, countless stars shine strongly enough to command attention. Rogue planets do not. They remain faint, difficult, and often hidden almost completely from view. But their silence does not make them rare in meaning. It only makes them hard to see. They drift where light does not gather easily, carrying their mass through the spaces between brighter things. In that way they belong fully to the galaxy, not as ornaments of starlight, but as part of its darker inventory, its unlit architecture of wandering bodies. And so the rogue planet continues, cold at the surface, warmer below, moving through deep space with no need to announce itself, held together by gravity, defined by time, and sustained for ages by the last inward stores of its own fading heat.